Good morning, everyone. Thank you for joining us. We will get started. My name is Luiz DaSilva. I'm the Executive Director of the Commonwealth Cyber Initiative, and I'm a professor at Virginia Tech. If you aren't familiar with CCI, we are an initiative of the Commonwealth of Virginia doing research at the intersection between security, autonomous systems, and data. And we have a mission that really includes both research and innovation and workforce development. This is really a statewide initiative, so it involves 39 universities and colleges from across Virginia and about 320 researchers. We're really happy to launch the first seminar series of CCI. And the way these are going to work is we have 4 lectures over the next 4 months, so in the fall. And all of them will be around a common theme. And the theme for this fall is artificial intelligence in cybersecurity. So I hope that you join us for all 4. And I'm particularly delighted that we're going to start with Dr. Nicholas Carlini from Google Brain. So I won't take any more of our time. I'll pass the mic to Professor Hongyi Wu, who will then introduce Dr. Carlini. Thank you, Hongyi.
Thank you, Luiz. So welcome again to the CCI AI for Security seminar series. My name is Hongyi Wu. I'm a professor and a director of the Center for Cybersecurity at the Old Dominion University. It's my honor to host the first talk of the seminar series. So if you have any questions during the talk, please feel free to type your questions anytime by using the Q&A at the bottom of your room window. And let me start with introducing Dr. Nicholas Carlini. Dr. Carlini is a research scientist at Google Brain, working at the intersection of machine learning and computer security. So his most recent line of work studies the properties of neural networks from an adversarial perspective. He received his PhD from UC Berkeley in 2018 and a bachelor degree in computer science and mathematics, also from UC Berkeley in 2013. He is interested in developing attacks on machine learning systems, and most of his work develops attacks demonstrating security and privacy risks in those systems. He has received the Best Paper Awards from ICML and the IEEE S&P. Those are the 2 top, most prestigious conferences in machine learning and cybersecurity. His work has also been featured in a few magazines and and news mediums such as US Times, BBC, and a few others. So without further ado, let's welcome Dr. Carlini.
Hi, thank you. Let me share my screen. You can see and hear everything?
Yes.
Great. So today I'm going to talk about stealing neural networks with what are called model extraction attacks and model stealing more generally. So again, I'm Nicholas. I'm very excited to be here. Thank you for inviting me. This is seems like a very nice forum to be able to sort of get a bunch of people together and have some nice talks. So to briefly set up the problem statement here, the setup is that we have some neural network that's deployed as some black box where we've already loaded the weights and the parameters into the model. And we're going to imagine that I'm allowed to make arbitrary queries of the model with arbitrary images, and then ask the model what the label is, or more generally, the probability distribution of outputs, and receive this. And the question is, are we then able, using this, if we're given the inputs, the architecture of the neural network, and the final predictions of the neural network, can we somehow solve for the weights? So this is sort of the setup. The question is, given query access to a neural network, can we extract the parameters? And there are a bunch of reasons to care about this. And so let me walk through a little bit of the motivation of why we might want to go about doing this. Before I do that, first, this is work, a bunch of which is not mine. This talk is based on mostly these 5 papers. I'll give you these references again at the end. If you're curious, there's a lot of good work in this space. So why should I try and steal a neural network? For this, I think there are basically 3 reasons. Actually, 2 reasons would be better to describe first. So the first is for theft. So for this, I might want to steal a neural network just because some other company does something that has a much more accurate model than my company does, and we want to steal their model because we want a more accurate translation system, we want a more accurate self-driving car, whatever. And so, like, you might just be motivated by having their model to do the thing that they're able to do. Alternatively, you could also care about stealing a machine learning model for reconnaissance reasons. And by this, what we mean is, I don't necessarily care about the model in and of itself, but I want to use the model to abuse it to do some other task. So maybe I want to fool some system's self-driving car in order to make it crash. And so the first step I'm going to do is steal the model. And then once I've stolen the model, I'll use it to generate an adversarial example and then cause the car to crash. And so the reason I want the model is not because I necessarily care about having the model in itself, but I want to be able to use it to do something else bad. And so we call this a reconnaissance motivated adversary. And so really there's these 2 reasons that you might care about stealing the model. Then there's the question of what I might want out of my stolen model. And you can see similarly 2 things here. You can see that I might want it to have high accuracy, where what I care about is that it solves the underlying task well, and that's about all. So in the self-driving car case, maybe I just care that I steal a model that that just is able to drive around well in most settings and roughly matches the accuracy of the model that I'm stealing. Alternatively, I might also care about fidelity. And what we mean by this is we mean I want my stolen model to match the predictions of the remote model, even when the remote model is wrong. And so not only do I want it to be roughly as accurate, but also I want it to behave the same and have the same characteristics of the other model. And finally, there's the question of how should we view this problem? And there's roughly 2 ways to view the problem. The first is to think of this as a machine learning problem, where I know that what's deployed is a machine learning classifier. And so we can think of this as a machine learning question. And basically, we want to learn our own function that approximates the remote function on most of the data distribution. The other way to think about this is through some mathematical direct analysis approach, where we just view a neural network as a mathematical function, and we're just going to try and analyze the properties of this mathematical function in order to figure out, like, directly what the parameters of it must be. And so the reason I've set things up in this way is that it turns out that these questions are all very connected. And if what I care about is theft, then I probably want a high accuracy model. And the way to go about this is with machine learning and thinking this as a function approximator. On the other hand, if what I care about is reconnaissance, then really what I'm going to be asking for here is for a high fidelity extraction. And I'm going to do this probably through direct mathematical analysis. And so this is really the setup of how everything is going to work. And most work in this space tends to focus on the theft and accuracy and machine learning side. I'm not going to talk about that so much. And the reason why is just because I think this question is fairly well studied. And I think it's interesting to try and think about this other motivation for why we might try and do these attacks, because it sort of gives some insight into how we might analyze machine learning systems without thinking about them as these big black boxes. So I'll say now that if you have any questions and you put them in the chat, and they're, like, related to the current content of the slides, that, like, something wasn't clear, please do that, and someone will interrupt me and ask the question. There is time for these sorts of questions. And then at the end, there will be time for various questions on implications of these kinds of attacks and just broader discussion. But if something isn't clear at some point, please do stop the slides then, so that we don't keep going when something isn't clear. Okay, so let's get started then with how we do this high fidelity extraction of neural networks. So the basic question that I posed earlier is, given this Oracle query access to a neural network, can we extract maybe the exact weights? This is sort of the best you could hope for, is to be able to try and just recover a bit for bit identical copy of the model. This would have the highest fidelity you could imagine. It turns out, though, there's a fairly simple theorem that shows that this is impossible. And the way this theorem works goes something like this. Suppose I had a network with ReLU activations that was just 2 layers. And I have the first weight matrix and the second weight matrix. And the way this is going to work is that I have, like the way that these machine learning models work is they're just matrix multiplies, followed by some nonlinear activation in the middle, followed by matrix multiplies at the end, where we're just feeding in and then feeding out weights along these edges. And so if I had a neural network that looked like this, that was matrix multiply, followed by ReLU activation, followed by matrix multiply, this would be identical from an input-output behavior to a neural network that behaved like this. That was A over 2, ReLU activation, and then 2B. Because when you multiply this through, you just get the same thing, product of A, product of B, and you're not going to change any other values. And so these 2 neural networks are identical. You cannot distinguish from an input-output behavior the function that has the weights A and B, and the function that has weights A over 2 and 2B. So the next question then is, if we know that this is impossible, can we modify our question slightly and ask to be able to extract a functionally equivalent neural network? Where the idea here is that what we want is I mean, there's some way to formalize this, where you talk about some epsilon delta definition, but basically all we mean to say is that they behave the same. If they have the same input-output behavior, we're going to say the functionally equivalent, even if their bit representation on disk is different. And this is the best you can hope for. Turns out, though, that there's another simple theorem, slightly less simple, that shows that you can't actually achieve this either. And the reason why you can't achieve this is a reduction from 3-sat. It's not a computational, we can guarantee you can't achieve it, but it shows that it's at least NP hard. And in order to be able to extract, I can set up this 3-sat problem where the only way that you can extract the network is if you can solve 3-sat. And so we know that's not possible, and so you're not going to be able to do, in general, this functionally equivalent extraction. But you know, that's like, it's not, we haven't yet lost all hope, because probably stochastic gradient descent is not going to learn these pathological worst cases. And so instead the question we're going to ask is, assume that we're given query access to a neural network that's learned typically through stochastic gradient descent. And the question now is can we extract a functionally equivalent model? Because while there might exist these pathological worst cases that are reductions from 3-sat, the likelihood of stochastic gradient descent learning such a sort of pathological case is very low. And so we might be able to actually extract networks that actually happen, even if there exist cases we know we can't possibly extract.
Hi, Nicholas.
Yes.
Do you mind we interrupt you for a quick question? There is a question in the chat asking, what is a 3-sat?
So 3-sat is one of the typical NP hard problems. And so you can, this is just the Boolean satisfiability over 3 variables. So I want you to verify, to check that the exact problem isn't too important. The only thing that matters is we know that this problem cannot possibly be solved efficiently. And I'm able to say that if you could solve this problem efficiently, okay, well, I guess the reduction goes the other way. But all we're saying is that we know that we can't solve the extraction problem. Because if you could solve the extraction problem, then you could solve this problem called 3-sat. And we know we can't solve 3-sat. There are proofs of that. Therefore, I know that I can't solve this extraction problem efficiently on all inputs. Yeah. So this is the setup.
Thank you, Nicholas. I think that's
Yes.
clear enough.
Yeah. Yes, and yeah, please do keep asking. These are good questions. If I've assumed something that that you don't actually know, please do ask. Otherwise, things will get they get more complicated, and it'll be harder to understand what's going on later. Okay, so the main result of a recent paper that we have at Crypto is to show that yes, empirically, this is actually something that we can do. And that these worst cases might exist, but this is something that we can do. And so the focus of this talk is going to be sort of working through the literature from roughly 2016 until Crypto last week, where and sort of covering how all of these kinds of attacks work. Okay, so to get started, let's start with this case of a zero hidden layer neural network, which is maybe a very boring neural network to consider, but it's just about the simplest thing that you could try and analyze. And this is some work by Florian Tremer, who's now at Stanford and really started this model stealing work in his 2016 using security paper. Okay, so the way this works is a zero hidden layer neural network is a very simple function. It has for example, three inputs. I'm just going to do three here for simplicity, but in general, an arbitrary number of inputs. And for here, just one output, but in general, an arbitrary number of outputs. And along each edge is a weight. Here we have weights A, B, and C. But if I'm actually going to be querying this, I don't know what the weights are, but I can feed in arbitrary inputs. And so what I'm going to do is I'm just going to say, well, I'm just going to feed in the inputs 1, 0, 0 and ask what the model is. It will take the dot product of 1, 0, 0 with the weights A, B, C, and will give me the output of A, because it's a relatively simple dot product and we just get A. And so now I know that the only way this could happen is if the weight A was on this edge. And now I can change my inputs a little bit and query on 0, 1, 0, and I'll get output B. And I can say, well, that must mean that B is on this edge. And then I can repeat the same thing and do 0, 0, 1, and I get out C. And so by doing this, I've sort of directly read off the weights of the neural network. Again, it's this sort of a trivial neural network. It's more like a logistic regression function, but you can basically essentially trivially read these off. And sort of the insight here is that even though this attack is trivial, we're not making sort of random queries and then going to try and learn a copy model that behaves similarly. We're making some very intelligent queries. Here, the intelligence is so difficult. We're making some intelligent queries in order to be able to read off the weights from this model directly. And in this case, you can see that the reduction I showed you earlier that shows that it's impossible doesn't apply. Actually, it turns out that you need at least 2 or 3 layers in order to do some of these reductions. And so these you can always extract fairly trivially. Okay, so this is how sort of the simplest case works, where you're trying to extract a neural network with no hidden layers. So now let's talk about one slightly more complicated version of this, which is to assume that we have one hidden layer. And in the case that we have one hidden layer, so the key assumption we're going to work with for the remainder of this talk is ReLU activations. So ReLU activation is just the max of the input and 0. And it's a discontinuous function, but it's discontinuous at only exactly one point. This is sort of the standard function which is used for all of machine learning. There are some places where you use different activation functions, but for the most part, this is the one that everyone uses, especially for image classification and those kinds of problems. Okay, and so for this, I'm going to show you some visual intuition. Again, this is work initially built on from some people at Berkeley at FatStar 2019, and then extended by an intern of ours at Google at using security this year. So the way that this works is I'm going to show you these one hidden layer neural networks. Again, I'm going to show, just for simplicity, 2 input neurons, 3 hidden neurons, and 1 output. Just again, because I want to be able to show these nicely. And in particular, it's important that there are just 2 inputs here, because how I'm going to visualize this is I'm going to show you points on a plane where each point here is going to correspond to an input to the neural network. Okay, so what do I mean by this? I mean, this is, so you imagine you're looking top down at what happens when you evaluate a neural network, where when I move along the x-axis, I change the value of the first input to the first neuron, and I move along the y-axis, I change the value of the second neuron. And I've color-coded the regions here so that each region is a linear region. So remember that if we have ReLU activation functions, that they're piecewise linear, And so they should introduce discontinuities into the input space. Now, if we only had one hidden layer, no hidden layers, this would be a completely linear function. And essentially what you're asking me to do is to recover the gradient. Now with one hidden layer, we have a slightly different, we have a more complicated loss surface. Okay, so the question is, why does it look this way? I'm gonna say, please stop and ask questions now if this picture isn't clear, because this picture is gonna be the basis of the rest of the talk. And so if it's not exactly clear what's going on, let me know. So what you should be thinking about in this is not necessarily that there are these 7 colored regions, but there are these 3 lines. And the reason that there are these 3 lines is that each of these lines corresponds to one of the neurons in the neural network. Where the idea is, for example, this middle line corresponds to this middle neuron. And I know that if I'm below the line, then I'm in one region of the activation of this neuron. And if I'm above the line, then I'm in the other region. So for example, when I'm below the line, maybe I'm in the part of the regime where the neuron is inactive. And when I'm above the line, it's active. And so because of that, when you cross this line, you have a discontinuity in the gradient, but the function is piecewise linear both above and below. And similarly for the other lines that I'm drawing through the input space. Okay, so this is the setup of the picture of what a neural network looks like if you were to visualize the input space. And of course, more generally, I'm not going to have these 2-dimensional slices if my inputs is not 2-dimensional, but I will have these higher dimensional hyperspaces with hyperspheres cutting through them instead of this plane with lines cutting through the plane. Now, the first observation that this earlier work makes is the following. So we can really write down in each of these regions what the signs of these neurons are. We don't know what this looks like ahead of time, but it exists. Like if you knew what the model looked like, I could write these positive, negative assignments. Where, for example, here I've shown that we have the first value of positive means that the first neuron is positive, or like on the upper half of the plane. And what I can do is I can take these and I can like zoom into just one region. And I can draw what the neural network looks like in this piece. So if this component was a positive, negative region, then what this means is that the second 2 neurons are inactive. And so they're not contributing to the output. And so this is just a completely linear function here that's only using the weights on these first 2 edges plus the weight on this final output edge, but isn't the weights on the other 2 aren't contributing at all. Okay, so this is really the setup of how everything is going to be looking when we're doing these kinds of attacks. And so the first observation is that the locations of what we call these critical hyperplanes, these are these lines in space that make the gradient discontinuous, almost completely determine the neural network. And the reason why this is the case is I haven't convinced you of this fact yet, but I will do that in just a second. And the reason why is that suppose that I had, oh, sorry, the animation went too fast. Suppose that I had some point that was on this critical hyperplane. And suppose that I knew what this point was, and I knew, then I could do the following. If given one of these points, here's what I can do. I'm going to take the XY location of this point, which are the input to the neuron. And I know that I have one of the inner hidden layers that's now at value 0. And the reason why I know it's at 0 is because that's the only point at which these functions have discontinuous gradients. At all other points, they're perfectly linear. So I don't necessarily know it's this middle one, but without loss of generality, let's just assume that it is. And I have something happening on the other 2 neurons, and I have something as the output. And I'm just going to discard all these values. They exist, but I don't really care what they are. Now let's imagine what happens if I step from x to x plus epsilon. Then everything's going to change. And I don't know exactly how it's going to change. In particular, u changes to u prime, v changes to v prime, and the output we get some extra linear term here. But importantly, the thing that I care about is that this inner neuron in the middle that was 0 now is something that we don't know. On the other hand, let's consider now that we could step along with step size delta along y and somehow get back to this value 0 in the middle. Again, everything else has changed. We're now at u double prime, v double prime, and the output is even more different. But now let's say that we get back to this value 0 here. Then what this means, it turns out that if we were to look at the values of the weights, if we call these weights A1 and A2, then the only way that we could simultaneously have x times A1 plus y times A2 equals 0, and also x plus epsilon times A1 and y plus delta times A2 equals 0. The only way that this equation could hold true was if we had that minus epsilon over delta was equal to A2 over A1. And this is sort of a critical observation, that what we've done is we've turned a couple queries on the inputs, learning these values of epsilon and delta, into a ratio of weights. And so while before in the previous attack that just directly read off the values, I could read off A and B and C by making some informed queries, I can't quite do that here and read off the values of the weights exactly, but I can read off ratios of these weights. So taking this back to the picture, what we have is we have this picture where we're taking a step of size, say epsilon along the x-axis and delta along the y-axis. And this is what gives us essentially the angle of this plane in the space. And I can do this for each of these planes here and learn their angles. The problem though is we're missing now some piece of information. And what we're missing is we're missing the magnitude of this vector. Fortunately, it turns out that this, like how big the vector is for a positive scalar actually isn't very important. And we can mostly ignore that fact. But the thing we can't ignore is that when you do these kinds of attacks, what you lose is you lose some sign information. And this is a critical piece of information. And the reason why it's important is that if you remember that the way these value activations work is they're going to be 0 in one region and active in the other. And if I get this, which side of this is 0 wrong, then I can't recover this through some other means. This is an important piece of information that I have to learn correctly. Now, it turns out that there's a nice way of recovering this. It turns out that local information is insufficient, that you can't just do some local queries. There will always be a global consistent view for any small local piece of information. There is some intelligent global query strategy that I'm not going to get into. But you can imagine how it works as something like this. I'm going to query the neural network on 4 random points, for example. And now what I need to recover is the signs of these three ReLU activations, the 3 ReLU activated neurons. And so what I'm going to do is I'm going to say, suppose that the sign assignment, just let me guess, the sign assignment was correct on all of them, and that they were positive, positive, positive. Then, if that's the case, is it possible to go and recover these 4 points? Basically, what I'm doing here is I'm running the layer n+1, the layer 2 extraction algorithm, using these 4 points. And if it was possible, then I would know that I guessed correctly. More than likely, though, my guess is going to be wrong. And it's not going to be possible to using these 4 points to recover an identical function to this, because I've already fixed all of the ratios on the first layer. And so what I'll do is I'll guess again. I'll guess maybe the answer is positive, positive, negative. And I'll ask if it's possible in this setting. It looks like there's probably going to be a question here. This is good. Maybe not. Maybe it's just someone connected to the audio again. Okay. If there's a question, please stop me. So the idea is what I'm going to do is I'm just going to essentially brute force this piece of sign information. Now, again, this is what I'm describing to you is exponential and is not efficient. But you can do better than this. But just for simplicity for the talk, this is what I'm going to be saying we do. And so the idea here is essentially what we've done is we extract the first layer up to this piece of sign information. And then we simultaneously solve for the sign of this layer and the values on the next layer. And it turns out that for the last layer, you don't lose any sign. And so you can run this attack this way. Okay. So finally, the question is that this whole attack presumed the existence of some algorithm that found these witnesses, these points that were on these critical hyperplanes. So the question is, how do you do that? And the way that this works is, again, another fairly simple algorithm. I'm going to draw a random line through input space, and I'm going to query a bunch of points along this line. And I'm going to look for cases where the gradient changes. And so the way to think about this is if instead of looking at this sort of top-down, looking at this sort of as a value of alpha between, as I scale from these points u and v on the space, and what I'm plotting here is the value of the function when you look at like u times alpha and v times 1 minus alpha. So this is linearly interpolating between u and v and the value of the function, the value of the neural network on the output. And what you'll notice is that there are going to be these different regions where the gradient is the same. And each of these corresponds exactly to one of the regions of the neural network. And the points at which the gradient becomes discontinuous are exactly the points where we have a ReLU for one of the neurons. And I don't know which of the neurons happened, but I know that there must have been a neuron that flipped from positive to negative sign at each of these points where the gradient is discontinuous. Because that's the only way that we can have the gradient change here. And it turns out that this sort of corresponds very directly to locations on these hyperplanes where we have this happen. And so this is how we identify these points on these critical hyperplanes, is we search on input space for discontinuous gradients. And we can do this with just binary search. And because I'll just check what the gradient is at point A, check what the gradient is at point B, and if they're the same, then I guess that they're in the same linear region. And if they're not, then I just split down the middle and then try the left half and try the right half and repeat. Okay, so this basically describes the full algorithm. What we do is we run this search to find one point, one witness to each of these critical hyperplanes. Then I compute the angle of the hyperplane, and that gives me the ratio of the weights. The absolute value of the ratio, I can just normalize to 1 without loss of generality. But then I have to recover the sign, and I recover the sign through this brute force procedure. And then once I'm done, I recover the second layer, and now I've essentially done everything. And so this is how you do the case of a one hidden layer neural network with two layers. I'll pause for a second in case there have been questions while I've been presenting this stuff so far. Okay, seems like not. Maybe.
Yeah, Nicholas, I think there is one question. Does it assume that the attacker has access to the model architecture and all the gradients during the probing? Yes. So the assumption here is that we have access to the model architecture. So you don't need this assumption. It's simpler if you assume that you know access to the architecture. But for the case of this one hidden layer neural network, the architecture is in some sense trivial. You just need to know the number of ReLUs that there are in number of hidden units. And you can recover this just by looking at the number of times. So if you draw a line in input space, if you were to go from -infinity to infinity along this line, the number of times that you crossed should be identical to the number of neurons. It's possible that you happened to choose a line that was actually completely parallel to one of these critical hyperplanes. The probability of that is very low, and so you can just imagine choosing 2 different lines and checking that you get the same answer. But the other question is, what's the assumption on the outputs? So the assumption on the outputs is not that I have gradient access, but that I have just raw access. So I'm not getting the classification as output. I'm just getting maybe the logic value as output, or the probability as output. And the reason why is, given the logic value, I can estimate the gradient just with finite differences. So whenever I need to be able to get the gradient, I can just do small epsilon delta queries in order to be able to recover it. And for most of these things that I've shown you, I don't actually need to be able to compute the gradient. I'm just saying that the gradient has changed so that, like, when we're thinking, we can visualize what's going on correctly. But most of what we're doing, for what I've described here, is talking about these finite-sized steps of epsilon and steps of delta,
or querying the input in order to compute these points here, you're doing linearity testing. So in practice, it's much more numerically stable to test for linearity than to check if there's a discontinuity in the gradient. And so in order to find these critical points here, what we do is I'll query 3 points and check if they're all on a line. And if they aren't aligned, then I assume that the gradient has been consistent throughout this point. But yeah, good question. Okay. So in general, how might we do this for a deep neural network that's not just one of these trivial one hidden layer neural networks? And I'm going to give you sort of the idea of how this attack works, but leave out a bunch of the details. So the way that this works is I'm going to assume that I have, for now, just for the slides, a 2 deep neural network. And this will work identically in practice for arbitrary depth, but I'll show you the case of 2. And so when we have this, what we're going to do is we're going to have a slightly different image that looks a lot more complicated to start. Like, it looks like there's a lot more going on here. But it turns out that there's not really. And so the reason why there's not is that whereas before there was just one piece of sign information that we had, which was whether or not like these neurons in the first layer were in the positive or negative regime. Now what we have is we have 2 pieces, where each region here corresponds to the sign assignments of one of the first layer neurons and one of the second layer neurons. And so we have these same 3 lines that cut the input space as before, but now there are these other lines that are cutting through the space that bend. And what's going on here is that these lines, if we were to visualize them in the input space of the first hidden layer, would be hyperplanes that are straight. But because what we're visualizing is the input to the neural network, which is modified by the first hidden layer, these second hidden layer lines actually bend in the input space. And so each of the lines here corresponds either to a first layer neuron, in which case it's just actually a straight line, or in general for neurons on the later layers, they bend as a result of their intersections with first layer neurons. And so this is sort of the fundamental difference of why this becomes harder for deeper neural networks, is that these lines are not straight. Okay, so in order to recover these neural networks, we're going to do essentially a similar process, but we're going to proceed layer by layer, doing the same thing as before. We're going to recover the first layer up to sign, and then we're going to recover the sign of the first layer, and then we'll repeat. We'll be able to peel this off and go to the next layer. So just like before, where we did one query through the input space, now we're going to do multiple queries and find a bunch of examples, we call these witnesses, to these critical hyperplanes. And the problem here is that now when we have these, I don't know which of these corresponds to neurons on the first layer and which of these corresponds to neurons on the second layer. And this is bad because we want to be able to extract only the first layer. So we ideally need to be able to identify this. And so how we do this, so just to make things simpler, I'm going to draw what the answer is, just what these lines are, just so we can visualize it easier. But how the attack is going to distinguish this is it's going to consider 2 pairs of these witnesses and ask, where is the normal direction pointing? And is it possible for there to be a line, a critical hyperplane, that cuts through these 2 points given this normal direction? Like, first, do the normals align? And second, if they align, do they align in such a way that we could have drawn a line through here? And the answer here is no, because these, like, you can't draw a line through these with these corresponding normal vectors. And then we ask, maybe what about this pair? And the answer again is no. And this pair, and the answer is no. And this pair, and the answer is no. And this pair, and the answer is no. And then finally we ask for this pair, and the answer is yes. And so we can learn from this is we know that the only way this could have happened is that if we had recovered 2 examples to the same neuron on the first layer, because otherwise we would have had something else happen here. And I can do this for all pairs. And this will let me read off essentially identically where these three critical hyperplanes are in input space. And it's possible, because we know that this kind of extraction is not guaranteed to always work because of these pathological examples I mentioned earlier. It's possible that we're extremely unlikely, or extremely unlucky. And in some unlikely event, what happens is we find 2 points that are very close to each other, are on a second layer neuron, but have this consistency property. And then we incorrectly believe that this is a first layer neuron. Now, the probability of this happening is very low by chance. And so what we can do is we can run this attack multiple times, and we should receive the correct answer almost always. And occasionally we'll get the wrong answer, and we can just discard the errors because they'll happen with low frequency. But if we had some pathological worst case, like if the person who designed this network was an adversary, then they could make sure that we couldn't possibly extract it using this algorithm by just making sure that we will make these errors with high probability. Okay, so this is what lets us learn where these critical hyperplanes are. Using the exact same procedure in the previous layer, I can then just directly read off what the ratio of these weights are. Again, the magnitude here doesn't matter. So the only thing I need to do is I need to recover the sign again. So how do I recover the signs of these first layer neurons? And the way I'm going to do that is the following. I'm going to use, let's see how much time I have. Okay, so I'm going to give sort of the intuition for how this works, just so I don't get too far into the details. But what I'm going to do is I'm going to find a neuron that happens on the second layer. And I'm going to know it's on the second layer because right now for a true hidden layer neural network, it's not on the first layer. And so I'm going to know that as a result, that I can recover where this line is in input space. And then I'm going to say, which possible configurations of the signs on the first layer could have admitted such a line cutting through the input space on the second layer. Because remember, there are only 3 real values which determine where this line is once we've fixed the first hidden layer and their signs. So what I do is I do essentially the exact same thing as before. And I say, for each of the possible sign assignments on the first layer, which of these allows us to have this line occurring in exactly this space? And only one of the sign assignments should allow it. And once I get that one correct, then I know that I've gotten the first layer sign correct. And now I can essentially just repeat the exact attack. I can peel off the first layer with the weights extracted correctly, and then rerun this attack exactly from there. And so this is sort of the idea of these kinds of attacks. So to briefly give some results on how this works. This is the big caveat, is that for small networks, so for shallower networks, you can do reasonable neural networks with hundreds of thousands of parameters. For deep neural networks, you can't. And the existing approaches work for like maybe thousands of neurons. So to briefly walk through what this table means, on the left I have the architecture. This is just how many input neurons and how many ones in each hidden layer. This is how many parameters that means you can, this is directly a function of the architecture. You can compute this, but I've just listed this here for simplicity. This is how many queries are necessary. The queries relate to the number of parameters. And then here are 3 different ways you can imagine measuring how well the extraction was. In all of these, smaller is better, where 0 is essentially perfect, where it means that the input, there is no difference between the 2 neural networks, and larger numbers are less similar and less good. And so, for example, for the 1 hidden layer neural networks, most approaches take roughly 1 million queries or so. For this 100,000 parameters, this is roughly, I think, 10 to 12 queries per parameter, but are able to extract very well. So like the state-of-the-art approaches that we developed recover neural networks that are identical, basically up to floating point precision, with 30 bits of precision on the input. But if you look at deeper networks, this is where like we currently don't have good approaches, where they work because we can extract them, but it takes like 1 million queries. And we can extract them to, again, maybe 30 or 40 bits of precision, but this network has 210 or 420 neurons, which is really, really, really small. And we can do this for the case of a couple thousand, but this is sort of the major limitation right now, is the scale of these approaches to deeper networks. And there's nothing fundamental here. Like the attack that I presented, in theory, does work for arbitrary size, arbitrary depth neural networks. It's just one of these engineering challenges now on being able to make this scale for deep networks, even in the case where you have something. I mean, the main problem is like floating point precision and these sorts of things that you have to deal with. Okay, so this was a lot of sort of depth. Now let me sort of come back up and talk about a couple of conclusions that I think are important as a result of the existence of these kinds of attacks. So first is sort of this general thing that has been going around since Florian's initial paper, which is that exposing prediction APIs leaks model parameters. And we know that for these, if you have a small neural network, that we can directly read off essentially bit for bit, almost an identical copy of what's going on. For larger neural networks today, we can't do that extremely well, but there's nothing fundamental prohibiting it. And so people who deploy neural networks should really start thinking carefully about either mitigation strategies to make sure that people can't just steal their models, or should be very careful to watch the state of the art in extraction attacks, so that when the attacks get good enough to work for the scale of neural network they're deploying, then they can start trying to figure out how to maybe limit the number of queries or do something to be able to stop these kinds of attacks from working. The second nice result of this is there's this field of cryptography called secure inference, which actually, despite the name, maybe isn't so secure. So what secure inference says is that we have a client and a server, where the client has some private input X and the server has some private model F of theta. Think here maybe hospital and patient medical records. So I have my medical records and the hospital has some machine learning model. And I would like to ask the hospital to run the machine learning model on my personal information without giving them my medical records. And similarly, the hospital wants to be able to run this evaluation without passing me the model itself. So I mean, right, so the trivial thing you could do is I could just give the hospital my whole data and say like, what's the result of this? And they could compute the output. And the other trivial thing to do is the hospital could give me their model and I could then I could evaluate on my machine. But we don't want to do either of these things for, in the hospital's case, other patient privacy, and in my case, my privacy. So what we're going to do with secure inference is it's this fairly complicated protocol, but the way that it basically works is like the two of us cooperate and through some way, and then because of the magic of cryptography, we both learn the output of the function without either of us learning what the other contributed as input. Sort of the problem with this is that as a result, there's this like secure inference does not hide any information about the function f that's revealed by the results of the predictions. And as we've just shown, the results of the predictions of a neural network completely reveal the function f. And so essentially what they're saying is, assuming false, secure inference is secure, but you could derive anything from that. And so secure inference is not meaningfully secure if we're allowed to do these kinds of extraction attacks. And so the field of secure inference is going to have to try and figure out how to build in some kind of defenses in order to prevent this, to allow secure inference to work in some meaningful way. Okay, so that's the second broad conclusion. And finally, to sort of briefly sort of give a high level sort of result, I just think that this model stealing and model extraction is a really interesting but understudied problem in secure machine learning. Florian's initial paper from 2016, despite being highly cited, was like not really extended for at least a couple of years. And the 5 papers that I showed you are some of the nice ones. It's going to be these set of papers that are, I think, very nice papers to look at for like where the state of the field is right now. And I'm kind of very excited by the possibility of these attacks, because I think that currently the people in security and machine learning are focusing on a small set of problems that are definitely important, but aren't all of the problems. And this is one where where clearly there's a reason for an adversary to actually try and run these. And I would like to be able to try and figure out more about how these attacks and defenses to these attacks work in practice. So with that, thank you, and I'd be happy to take any questions.
All right, thank you very much, Dr. Carlini. This is a math-intensive and theoretical work, but you make it so easy for everybody to follow. I really appreciate that. We do have a few questions, pop up in the Q&A window. The first question is basically about the complexity of the attack, and especially about the number of those critical hyperplanes. So is there an estimation about the number of those hyperplanes that we need to work on, need to figure out?
Yes.
Yeah, I see that the audience ask, if the number of critical hyperplanes is the number of layers multiplied with the number of neurons.
Yes, so that is the answer. The number of hyperplanes is the number of layers times the number of neurons. So there are two basically state-of-the-art attacks. The first is, and they're both almost identical. So what I described to you right now applies almost exactly to the attack that's at the bottom here, this cryptanalytic extraction, the one that I've worked on, and also this reverse engineering on deep value networks, which is by Rolnick et al. We both sort of independently came up with essentially exactly the same procedure, with the following caveat. Ours is more query efficient, but requires much more compute time to run. Theirs is less query efficient, but is more efficient to run. And so, I mean, there's an obvious question, can these two approaches be merged? Probably yes. But you can have various trade-offs in how these things work. And in general, the hypothesis that's not proven anywhere is that if you have an arbitrary neural network, which is learned by stochastic gradient descent, and is not one of these worst cases, then we think that it's polynomial in the inputs, in the size of the model. But we can't prove that, and we don't know what the polynomial is. But we believe that it should roughly be linear in most cases. But this is one of these areas of research that's very, we don't know very much about it. And so this is why I sort of want to talk about this, because I feel like there are some very basic questions on what is the efficiency of this algorithm that we have hypotheses, but we have no actual analysis for.
All right, thank you.
Yeah.
And another question is quite related, is about the number of queries that we need for a very large network. For example, those modern VGG16, that kind of networks. Yep. Do you have some kind of rough order of magnitude? Do we need, for example, 1 million per layer and things like that?
So it looks like we think that the answer, so our relatively efficient algorithm requires, I think, 100 queries per parameter for these neural networks which are fully connected. The hope is that for convolutional neural networks, which have a lot more structure, there's going to be a much more efficient algorithm for them. And I think this is the case. And the intuition is that you could express a convolution as a big giant matrix multiply, but that would be a waste of both time and space. And because we know it has this additional structure, it might be possible to recover the weights of a convolution much more efficiently than of one of these fully connected layers. And there are some ideas here, but again, no one's published anything. But yes, this is one of the big limitations. Again, ideally, information theoretically, 1 query per parameter should be sufficient. And so we're still 2 orders of magnitude away from what information theoretically we know we should be able to do.
Good, good. Now, we also have a couple of questions that are related to the model compression. So does model compression, kind of impact this attack? Does it make it easier or make it harder? Any, insights into that?
Good. No, this is a very nice question. This is one of the problems we're actually thinking about right now. The idea is that model compression should make it easier. So suppose that we had the trivial model compression of just pruning weights that were small. This just reduces the number of weights in the neural network. And as a result, I now have to do less work because there are fewer weights in total. Or you can imagine that if I say that my weights aren't going to be stored as float 32 values, I'm going to store my weights as integers. Now this again makes the adversary's job easier, because now I don't need to recover. If I measure a weight as this weight is 1.0001, I know the answer is actually it was 1 and I just got some floating point error. And so this makes it much easier to extract deeper networks, because I can do my extraction attack and then project it onto the set of valid weights. And now I can have a much easier extraction attack. And so, like, yes, this is sort of the problem, is a bunch of these things that we might want to do in practice, like add convolutions, add compression or quantization, actually make the attacks easier.
Great, thank you for the in-depth answer. We have another couple of questions, basically on the defense side. So what we can do, right, to defend such attacks? For instance, if we introduce random noise at the inputs or the intermediate layer, does it help to kind of serve as a countermeasure to this kind of attacks? Or when we train the neural networks, is there anything we can do to make the network more robust against such attacks? Yes.
So the answer to the first question we know is yes, where currently the attacks don't work well if you add randomness to them. And in principle, you could average out the randomness by taking multiple forward passes and then trying to compute the mean. But this would sort of increase the query complexity fairly significantly. Alternatively, you could try and do what some other work does that's not what you mentioned, is try and do some detection strategy. So I'm going to monitor all of the queries. I think this paper is called PRADA, which is like protecting deep learning against model stealing or something. And what this paper does is it monitors the queries that are the inputs and tries to detect if this is like an unusual query pattern. And if it's unusual, then I just stop responding. I say, it looks like you're doing an attack. I'm just not going to give you answers. As for training neural networks to be harder to extract, I haven't seen any work on that, but that's an interesting question, I think.
All right, thank you very much. There are more questions, but we are running out of time. Thank you very much, Dr. Carlini.
Sure. I just say, if you have questions, email me, and I'll be happy to respond to over email. My email is just my first name at my last name.com.
Wonderful. Yeah. Well, what an exciting talk and wonderful Q&A. On behalf of CCI and all attendees today, thank you very much for your time, and we look forward to your new and exciting work, and we hope that we can invite you back to our seminar series again in the near future.
Yep,
and also,
good to be here.
And thank you everybody for attending the seminar. I think this is a fantastic way to kick off the new semester, and stay tuned. We will have 3 more talks from September to November. Dr. Carlini, if you can stop sharing, let me just quickly share one slide about our next seminar. It's going to be in September, end of the September, Friday, September 24th. The speaker is Dr. Giuseppe Attinis. He's a Faber Endowed Chair and also the Department Chair of Computer Science from Stevens Institute of Technology. He's going to talk about again, interesting topic that is relevant to AI and cybersecurity. The topic is AI taking over the world? No, but it make it less private. I hope that by the end of September, this answer is still no. If we change it to be yes, that we will just need to run away. So thank you very much, everybody. Again, thank you, Dr. Carlini, for this exciting talk.